Welcome back. Let us get to the lecture number 9. Let us bring in solution formation, either solid solution or liquid solution, and we would concentrate on ideal solid solution formation, ideal solid solution or liquid solution formation. Now, in the beginning we have considered two metal A and B, and we considered that both of them have same crystal structure. And we also assumed that they can be mixed at any proportion. Means we can vary the concentration from pure metal A to pure metal B, the entire range we can have solution, and we are also assuming that they would form ideal solution. Whether it is solid or liquid, it does not matter, but the entire concentration range will form ideal solution, which is a kind of a crude assumption which cannot be true, but since we are dealing with ideal solution, the simplicity aspect of it, we can assume that. Now, we say that these are the assumption for both cases. Now, I say that in the beginning I have Na number of A atoms and Nb number of B atoms, and we are considering that both of them are solid, and both of them are solid means the temperature at which we are considering the solution formation must be less than Tm of A and Tm of B. That means the melting point of A and melting point of B at a pressure 1 atmosphere. We are fixing this pressure 1 atmosphere. Whenever we mix them, it will form solid solution. And here also we are considering that they would form random solution, and also we would have a complete disorderedness in the system. That means there will be no preferred sites for A atom and B atom in that solution. So, random solution and no preferred sites for A atom and B atom. And another thing we are considering is when we add this Na number of A atoms and Nb number of B atoms, they will be same as Avogadro number, and whenever we consider Avogadro number, it means this is 1 mole. Now, if we consider that we are considering 1 mole solution formation, I can also calculate what is the mole fraction of A and B in the solution. Simple, I can consider XA and I consider XB, which is the mole fraction. Here it is equal to Na by N0, here it is equal to Nb by N0, since the total addition, total number of atoms would be N0, and this is mole fraction. Now, once we have this picture, then we have to consider a free energy change. We have already seen that for any process, whether it is a solution formation or whether it is a melting, we need to have a gradient, and that gradient, the energy gradient, should be negative, and that actually supplies the energy for the formation of solution or the formation of different phases from another phase. So, we have to see change in G, which is del G. Whenever we consider that, I can also take it back, and I can also consider one more thing, that whenever I consider a pure metal, it is also having its inherent free energy, and I can take it as G A, and here I can take it as G B, and since the pressure is maintained at 1 atmosphere, I can consider it to be standard free energy in solid. So, I am not writing this particular term solid, but whenever we consider liquid solution, that time we have to notify this, whether it is a solid standard free energy of pure metal or liquid standard free energy for pure metal, and we are here using standard, means we are specifying the pressure at 1 atmosphere pressure. Now, so before mixing we have A with a free energy GA0, and we have B with a free energy of ZB0. This 0 superscript 0 means it is a standard state, and here we have XA mole of A, XB mole of B, and if this GA0 as well as GB0 are termed as joule per mole, then before mixing I can count what is my total free energy, which is G1. I can say before mixing is equal to XA GA0 plus XB GB0. And since the unit for both the standard free energy for pure A and pure B is joule per mole, so this becomes my total free energy. And if we combine XA and XB, it would become 1 mole. So, that you can also say that this is for 1 mole of total A and B. Now, after mixing, so now we are mixing them together, we are forming solid solution. It would, once it forms solution, it would go to a different free energy, and that time this would be, this can be written as H2 minus TS2, and can we not also write it in the form H1 TS1, means the H1 is the enthalpy before mixing of the total A and B, but they are separately considered, and entropy of A and B separately. And the temperature, as we have mentioned already, this is the temperature where we are trying to mix them and mix up. Now, before mixing, this was my free energy, which is G1, and after mixing, this is the free energy of that particular solute solution is G2. Then what is the change in free energy for the formation of solute solution? Is G2 minus G1. which is equal to del G. And now, since this particular difference is coming due to the solute solution formation because of mixing, I can simply mention it as del G mix, which will be equal to H2 minus TS2 minus H1 minus TS1. This can be simplified, H2 minus H1 minus T S2 minus S1. And if this is written as del G mix, I can also write in this form del H mix minus T del S mix. Therefore, I can also write G2 as del G mix plus G1. So, now if we consider this part only, I can write this. And since we are dealing with ideal solution, what would be the value of del H mix? It would be 0. Therefore, I can write it as G1 minus T del S mix. Now, let us quantify, let us expand this del S mix. Let us see whether we can write in the form of mole fraction. Now, whenever we are mixing A and B, these are pure A and B, and it has got a crystal structure, though they have same crystal structure. So, they would have their own entropy, and from Boltzmann consideration we can write entropy in this form, K ln omega. K is the Boltzmann constant, which is 1.38 into 10 to the power minus 23 joule per Kelvin per mole. Now, this omega is number of independent distributions. When we consider there is a constant volume and a constant internal energy, it is coming from statistical consideration of distribution. So, that time if it is a pure metal and if there is no impurity, so how many ways we can distribute the metal A atoms? There is only one way of distribution. Similarly, here it is one way. So, omega is equal to 1, omega is equal to 1 in both the cases. Now, if I try to mix them together and get AB solution, it would attain an entropy which is 2. So, in the beginning the entropy was S1 equal to S A plus SB, and S2, that means if I consider S2 minus S1, so it would also can be written in the form of ln omega solution. So, I can write it as S2 minus SA minus SB. Since this is ln K ln omega solution minus this is 1, this is 1. So, this becomes 0, this becomes 0. So, it ends up, and this is what in the previous just here we have seen that this is nothing but del S mix. So, this is del S mix. Now, entire attention goes into this particular quantity omega solution. Now, we have Na number of A atom and Nb number of B atoms. In combination, they are forming N0 number of A plus B. So, then I can write omega as N0 factorial Na factorial Nb. If I put it back, this can be written in this form. We can use Stirling approximation, which is ln n0 factorial. It can be written as n0 ln n0 minus n0. Like that, we can also do it for ln na factorial and ln nb factorial. And this entire thing is coming from the mixing of two different species at a particular temperature, because we are fixing the temperature. Now, we can write it as now we see that Na plus Nb, they are actually nothing but N0. So, I can cancel out these three quantities. Then we are left with Nb. Now, here K N0 I can write in this form, I can write this, I can take the minus out and then write as we know that Na this quantity is nothing but x A and this quantity is nothing but x B, and then further I can take N0 and form Na N0 ln x A plus this is also x B, this is x P, this is x A. So, I can write, and what happens to this quantity? This is Boltzmann constant into Avogadro number, which leads to universal gas constant, and then it becomes x a ln x a plus x b ln x b. So, finally, we can write del S mix equal to minus R x a ln x a plus x b ln x b. Now, I can go back to this original equation. This becomes G 2 equal to G 1, and since this is nothing but T del S mix, so I replace G 1 and del S mix and put this one for del S mix, and so if I replace them, x b. So, I just do little adjustment, x a this one is nothing but chemical potential of A in that solution, and this one is nothing but chemical potential of B in that solution, that means in that solid solution of A and B. So, I can further write it as mu B. This is an important, very important equation, which tells what would be the free energy if we mix x a and x b at a temperature T when pressure equal to 1 atmosphere. So, that means that is the point, that free energy point. We can also make out the physical aspect of G 2. Physically, we have to understand what is this G 2. We have to see the graphical representation of all these equations. So, this equation, we have to see the graphical expression, we have to see this, and we have to also see this. So, this is coming from S del S mix and this as well as this. From the graphical representation, we can also get to this, and that would give clear cut picture how physically this G 2. Now, if I try to see this, let me again rewrite those equation. G 2 equal to x a mu a plus x b mu b, G 1 equal to x a G a 0 plus x b G b 0, and del S mx equal to minus R x a ln x a plus x b ln x b. And here mu a is basically the chemical potential of A in solid solution, and mu b is basically the chemical potential of B in solid solution. Now, if I try to plot, let us see how the plot look like. Let us say this is 0% B, 100% A, this is 0% A, 100% B, that means these two are pure end. If we try to see their mole fraction, this is 1, this is also 1, here the mole fraction of B is 1, here the mole fraction of A is 1. And if I try to see the mole fraction of B varying in this way, so gradually the mole fraction of B would increase from 0 to 1. So, now here if I try to see GA 0 position and GB 0 position, so then this 2 are two extreme points when the mole fraction is 1 for A and mole fraction of B is 1 when it is GB 0. Now, if I try to see this equation is simply a straight line equation. Here this is G1 equal to XA GA 0 plus XB GB 0. And now, if I try to plot this one, then we will see that this plot would look like, and this is del S mix. And I can also write this G2 as G1 plus del G mix. Since it is ideal solution, then I can also get the knowledge of del G mix, which is nothing. This would become minus T del S mix, because del S mix, if I consider this particular thing, these are fraction, so it will be negative, and there is a negative term, so it would become positive. So, del S mix is always positive, but if I multiply with the minus T del S mix, so it would become negative. And here, since del H mix is 0, which is the enthalpy of mixing because of the ideal solution, this becomes del G mix. So, now we have drawn this equation as well as minus T del S mix we have plotted. We will take it up in our next lecture and complete this entire picture, and then it will be clear the significance of G2. Let me stop here, we will take it up in the next lecture. Thank you.